And now we'll move on to today's speaker, Nir Badt. He did his BSc and Masters at Ben-Gurion University, and his Master he did with Yossi Chatzor. Afterwards, he went on to do a PhD at Brown, and from the 2022 to 2025, he was a postdoc at the University of Pennsylvania. Since last year, he's been at Jesse Helmholtz Center for Geosciences in Potsdam, and he'll be telling us about the research he's been doing recently. So let's take it away.
Thank you. Well, I have to say that my affiliations, current affiliations for and foremost, and here at Fuji, I'm working with Inaka Aronov and Einstein project, but also with Jonathan Ellis. But today I'm going to talk about the work from my first postdoc at the University of Pennsylvania, with collaboration with researchers in Texas A&M. And I'm going to talk to you about scales today. And I'll talk why small scales are important for things that we're thinking about them in large scales. So we'll start off with just talking about some broad questions in earthquake physics or fault mechanics, or whatever you want to call this branch of geoscience. But we really, there are some things that we know with more detail and some things we know with less detail. But I put like about 4 questions up here, which are just definitely not all of the questions. We want to know what controls the earthquake rupture size, the timing, and location. I mean, that'd be pretty good from our perspective. We also want to learn things about how faults evolve through time and through repeated earthquakes and the seismic cycle. Moreover, a question that sits in the back of the mind of every experimentalist, including me, is, do our experiments actually scale up to the fault scale? Right? That's a big question that we must always try to keep in mind. And furthermore, what dictates the broad spectrum of fault slip behaviors as we see? There's slow slip events, creep, tremors. These types of events are all type of earthquake behavior, but they are dependent on very different mechanisms. And I try to tackle and approach these types of questions using a 3-pronged approach, using skills and knowledge from geology, and rock mechanics, and material science. And the talk today is going to utilize all 3 of them. Maybe going to be a little bit on the material science part of this realm, of this approach. But I really try to identify the physical mechanisms and chemical mechanisms that control fault and rock behavior by designing experiments that look into and constrain theory and try to bridge the observations I make in the laboratory with observations that are made by field geologists at field scale and leverage that with modeling from theoreticians. Just a few notes about me. I'm mainly an experimentalist. I'm just an experimentalist, I would say. During my PhD, I worked with a rotary shear apparatus here at Brown University. I also worked doing experiments during my master's with Yossi Chatzor in Ben-Gurion. I mainly deal with friction, how it evolves during rapid slip or subseismic slip rates. And I also delve into some modeling where I look at thermo-hydraulic mechanical coupling during earthquakes and faults. I look at how roughness changes and evolves and controls the fault behavior during slip. And I'm also interested in processes like energy dissipation in geological materials that are more relevant to broader geophysical questions. And today we're going to focus more on the small scales and look at micromechanics, which is the work I've done during my postdoc at Pennsylvania. The long-term goal that what I'm working towards, or what I want to work towards, is really trying to build a unified theory, or unifying framework that connects grain scale processes, friction, deformation, up to the fault scale, seismic cycles, and eventually try to get a better estimate and constraint on the associated hazards with these types of phenomena. Okay. Let's start off by talking about the seismic cycle. So, generally speaking, we can say that a fault that generates earthquakes would follow more or less this kind of behavior. This is a figure from Di Toro et al. From 2012, and we have time on the x-axis, and on the y-axis we see the fault strength, which is just the resistance to slip or the displacement of the fault itself. The shear stress, that's what's the traction, what's the on the fault surfaces and the fault itself. It's mainly from tectonic loading, and the subsequent slip or displacement on the fault. This is accumulated displacement. So long as the stresses on the fault are smaller than the fault strength, then there's no slip. Maybe there's some creep, time-dependent creep. It's really, really slow. We don't really feel it. We can measure it, but not feel it. But once the shear stress increases over time through tectonic loading, it reaches the strength of the fault. Then we nucleate an earthquake. The earthquakes are depicted by these stars. And we start to dissipate and relax all the energy that we accumulated during the pre-earthquake time. And the shear stress relaxes because we're just dissipating the energy. The fault strength also decreases to different processes, basically breaking up and rupturing the fault itself. And we accumulate quite a bit of co-seismic slip during this earthquake. And once the earthquake stops, we used up all the energy available to us. Then we see that both the shear stress start to increase again over time, and we see post-seismic healing. And this goes on and on through repeated earthquakes, some big, some small, over time. What I want to focus today is the healing part. It's not as dramatic as the earthquake itself. It's interesting. Yes?
What is the time scale on this?
So, that's a good question. We typically, we can say what the average time between earthquakes, but it can change dramatically. It can be thousands of years. It can be, it really depends on how big the earthquakes are, right? Like the San Andreas fault will slip every day in different locations, and it can be very active. So it really changes from one tectonic setting to another. This time scale could be thousands of years, millions of years, or even months. Okay, so why I want to focus on healing? Well, a few things why it's interesting. First of all, the amount of slip and the spatial extent of the earthquake is dependent on the healing. The stress drop, the amount of stress that is reduced during the earthquake, is also dependent on the amount of healing. These two actually are how we calculate, broadly how we calculate the earthquake's magnitude. The recurrence interval, that's the average time between earthquake events. Also dependent on the healing. And also from laboratory experiments that show, people like Greg McClaskey show that even the high frequency contact of the radiated seismic energy is also dependent on the healing processes in the fault. And also the rupture style itself and the dynamics. So there's a lot of work going into healing and how it affects different observations of phenomena related to earthquakes. But the first question we need to ask ourselves is, what exactly are we talking about? What is healing? If we take a look at this fault this is a very localized fault from the Apennines in central Italy. The fault itself, you can see there's a discontinuity over here. If we look close up of the architecture of the fault, it's a localized fault. And we can see different rheologies, different mechanical units. We have the crushed rock in the cataclysite, a highly deformed crushed rock like ultracataclysite, and some calcite veins, and more competent rock. And all these types of rocks, deformed rocks, they have pore spaces in between the grains. There are grains, crushed rocks, fractures, and rock contacts, which basically surfaces are touching and connecting to contacting each other. We will distinguish between two families of processes that make up healing. The first is aging. That's basically the frictional re-strengthening of rock contacts or rock surfaces. Think of the grains inside this cataclysite. They're touching each other. Over time, they get compacted. They get more and more contact. Something happens with the contacts themselves. That's what we call contact aging or frictional aging or aging. The second process is cementation, where all the pore space between all the grains and the cracks themselves gets filled up by secondary minerals from precipitation. This can be quartz or calcite minerals, and they kind of cement the whole rock mass together and make it a bit more competent. And so these work together, but they work at very different time scales. Where cementation occurs over long time scales of months to years and decades, aging actually occurs over shorter time scales from hours, days, and a few weeks. And I want to focus on aging because it's a friction-related process. What do I mean? It changes the friction coefficient. And that means that as we go deeper and deeper into the earth, we have higher and higher normal stresses and pressures acting on our faults, then the contribution of aging to the strengthening or re-strengthening of faults is going to be significantly higher than cementation. So not that cementation is not important, but that's the focus for today, the aging. So moving from the field to the lab, how do we quantify and measure aging, or frictional aging? We do that through slide tests. Now, these are not meant to mimic or simulate the seismic cycle per se, but we're kind of doing it at slower rates, and we're learning something about the physics and what happens in rock friction through these experiments. So think of this great block sitting on this striped surface. I guess every friction top has one of these diagrams, and the block is moved and slid across the interface between them. And when we move it at a constant rate, we're going to get at some point to kinetic friction, or if you want to call steady state friction, where the friction doesn't change over time. When we stop pulling on the block, friction is going to relax. We're going to go into a hold, kind of like in the interseismic period between earthquakes. During that time, it relaxes for a predetermined time that we choose, and then we resume sliding and pulling on the block. That's when we see a sharp increase in the friction coefficient, reaching a peak, before resuming some steady state friction later on. This change, this difference between the peak and the steady state friction, that's delta mu, is that what we call and quantify as frictional aging. Friction is kind of like a broad and elusive term, but if we think of what exactly is friction, we know that every contact, whether it's nominally flat or polished, will always exhibit some roughness at some small scales. So even this seemingly flat contact would feature this topography where we have these peaks and valleys, and actually the solids, the top solid and the bottom solid, actually interact and touch through these topographic maxima. And we call each of these contacts an asperity junction or asperity, because each bump is an asperity. And the friction force is actually the summation across all the asperity contacts, and it's dependent on the inherent shear strength of the contact times the contact area. So just keep that in mind. That's friction, and it's controlled by these two parameters. And we'll start looking at what happens from previous experiments and studies on slide-on-slide tests. What they found is that delta mu, remember, the frictional aging increases linearly with the logarithm of hold time. So for longer and longer hold times, you see an increase. That means you're kind of seeing a healing or an increased frictional resistance dependent on this time. And it's linear. And this is true for a whole range of materials, whether we're talking about granites, carbonate rocks, crushed rock, glass, polymers. This is true and works well with many different types of materials. So it looks like we're capturing some general physics here that control this process. So remember, frictional aging grows linearly with logarithm of time. Why is that? Well, people typically think of that in terms of contact area growth. The idea is that, remember these small asperated contacts, because they're quite small and we have quite a bit of load on the block, then they can deform plastically. What do I mean? They kind of squish and change shape, and by changing shape, the contact area actually increases. If we idealize one contact as this sphere on this rigid flat, then at the beginning of a hold, then the contact is pretty small, contact area is pretty small, but over time, the sphere is going to squish, contact area is going to increase, and that means contact area grows. So when contact area grows, friction grows as well, and that's why we see this frictional behavior. Contact area grows linearly with a logarithm of time. This comes from the seminal work by Dietrich and Kilgore. It's a fantastic work, and that seems like the plausible explanation for why friction increases with a logarithm of time, right? And so, that's a really nice physical framework. It works well with different materials, and so it's widely used and accepted in friction community and in the earthquake modeling community. The idea is that the approach, the hypothesis, the contact area growth mechanism controls the frictional aging, goes into and explains almost all the experimental frictional studies today or in the past 20 or 30 years. It also is the physical basis for almost all earthquake rupture and today more and more landslide models. These are models that are super important because we draw conclusions about seismic hazards from these models, right? This is our best means to try to estimate what will happen in the future, or what will happen if certain criteria are met. The thing is that what goes into these models, which is based on the experimental work, can lead to very different conclusions or circumstances. This is from Ampuero and Rubin from 2008. They used the main two friction evolution laws that are used today. And if you know rate and state friction, then you know these two laws. The aging law is basically the formulation that relies on contact area growth. The slip law, we don't need to go into what that is, but it's another formulation. When you use, for the same fault, same conditions, but use different friction laws or friction evolution laws, then you can get a very different slip behavior across a fault over time. Each grows over time, depending on the friction evolution that you put into the model. Same thing goes into the velocity measurements or the velocity profile in a fault during an earthquake. That means that what we put into these models is really dependent on the physics and the friction behavior that we know from the lab. And the thing is up until now, we only use the contact area growth mechanism from a few experiments which are very, very good, but are done at room temperature conditions. So that introduces a lot of uncertainty when we go into more complex geological settings where where we have fluids, we have different mineralogical species, we have complex chemistries, we have higher temperatures. So we're using a simplified physical mechanism like contact area growth, which is great. We're introducing some uncertainties into these models when we go into more complex environments. And I will close this slide and say that even by using this physics-based aging law, or the contact area growth, we still cannot explain the full range of slip behaviors we observe in the lab. So the second mechanism, which goes into the friction force, that's the contact strength, as I said. The mechanism for that is chemical bonding. Up until now, we saw that we don't really need to talk about chemical bonding, because when we have contact area, then yeah, obviously there's maybe chemical bonding. Maybe that's how people approach that. So excuse me, all the people who care and study carbonates, but for the rest of the talk, we're going to talk about silicon oxide, because we live in a silicate Earth. And silicon oxide is silicon with 2 oxygens, and it's crystalline form we call quartz, and its amorphous form like glass we call silica. And we take these 2 blocks again, they're both made of silicon oxide, and studies have showed that when these two, when a small scale contact between these 2 types of solid occurs, then silicon oxygen silicon covalent ridges form across the interface. That's chemical bonds right there. And atomic force microscopy studies done the same slide tests that we looked at before, and they concluded that frictional aging comes from the chemical bonding and not just the contact area. These silicon oxygen silicon bonds are really, really important, and that's what controls the frictional response. And that is completely missing from all the models that are typically used in earth science to model earthquakes and also landslides. Okay, there's a problem here. Geologists like to think at different scales. Small scales, looking at thin sections, up to field scales and faults hundreds of kilometers long, thousands of kilometers long. That's why scaling from the AFM test, the atomic force microscopy test, into fault mechanics and earthquake science is really, really difficult. We're actually saying, yeah, we have some very unique and interesting observations at the nanoscale. But these nanometer scale contacts from the atomic force microscope, that's where atomic intermolecular forces live. That's the scale where they are important. Are they really important in bulk mechanics that we see in faults? Second, the contact stresses from these tests is really, really small. There's no plastic deformation, so obviously there's no contact area growth in these experiments. And lastly, these types of tests are really, really sensitive to the environmental conditions, changes in humidity, temperatures. If the person making the tests had lunch and washed his hands or her hands, there's no way that they got all the leftover food from their fingers. I'm talking about like really molecular level hydrocarbons from sandwich. And they touch the sample, that's gonna come up into these friction tests at the nanometer scale. They're really, really sensitive to the surface chemistry. So they don't scale easily. That's where nanoindentation comes into play. Nanoindentation is really, really cool and really fun. And this is a diagram of a 2-axis nanoindenter where we have this aluminum frame, we have these 2 force heads, a normal force head connected to the tip, which goes into the sample, and another force head in the lateral position that can translate this tip across the sample. The tip is typically made out of diamond. This is an SAM image of the tip itself. It's small. But once we indent, this is a Berkovich type tip, a three-sided pyramid. When we indent, we leave a mark because we cause plastic deformation. You can see the scale here, 5 microns. And this instrument allows us to do scratch or friction tests. We can also do uniaxial loading, unloading tests. We can control the tip geometry. You don't have to use this type of geometry, this three-sided pyramid. You can use a flat punch, a sphere, 4-sided pyramid. And we can also control the tip material and obviously the sample material itself. So we can test different chemical environments, chemical contacts. And lastly, I would say that there is very high precision controlling this instrument. It's called a nano-indenter because we can control displacements down to the nanometer level. We can move at a nanometer per second rate. We can move in displacements of a few nanometers. That's why it's called nano-indentation. The contacts themselves are bigger, so don't get confused from that. So we have a very highly precise instrument that can allow us to test these types of questions of contact mechanics and contact chemistry. And I'll elaborate more and say that it's great for those types of studies, because for our interests of faults and earthquakes, the contact area in the nano-indenter contacts is comparable to the small-scale roughness or small-scale bumps on natural faults and experimental faults. What do I mean? So look at this diagram over here. We have power spectral density, which is kind of a measure of roughness or the amplitude of a bump of a rough surface, and the wavelength, basically a length scale. Prior works from Amir Sagi from GSI, which done a lot of work into roughness and how it changes. He made measurements. They made measurements from natural faults. This is from his paper from 2007. This is in Nevada. And they showed that the roughness actually increases, the amplitude of the roughness increases linearly. This is a log scale, as we look at larger and longer length scales. Tom et al. Also went down and looked at the same at different fault surfaces, natural fault surfaces, and got the same relationship down to these length scales. I also got roughness profiles and measurements from experimental faults. These are these dashed lines. You can see I overlaid the contact, the wavelength of contact of nano-indentation contacts, and they fall really nicely on the experimental faults and on the lower end of natural faults roughness. So we're basically looking at things, testing things in the lab that are relevant to natural faults and experimental faults. Second is that I said this before, the contact pressures using nano-indentation can be quite high, really, really high. We can reach about 11, 12, 13 GPAs. And that doesn't mean anything to you. That's about the normal stress that acts on a piece of rock at a depth of 400 kilometers into Earth. And obviously, we're not thinking about this, but 11 GPA is about what a small contact, rock contact feels in the fault, buried in like mid to lower crustal depth. Okay. I would also add that contact area is continuously monitored during an experiment. And that's something that all of the large-scale or mesoscale rock friction tests or experiments, they can't do. You just can't do because you can't do it continuously during an experiment. But there is this nice paper from Oliver and Farr from '92. It has like 33,000 citations. And they kind of invented the whole thing, and it's widely used today in material science, but is hardly ever used in earth science. And I think that's really an open playing field that we can change and start utilizing this instrument more and more into friction studies. So we have a really good instrument that can provide us a lot of information, high quality information that is typically lacking in traditional rock friction experiments. Okay, let's start off with doing some slide tests with a nano indenture. We're running diamond on quartz, a diamond tip on a natural quartz sample, and that's the tip. And we can scratch the surface. You can see I can make the scratches really over going around any heterogeneities in the sample itself. And scratch it. It's really high precision, and you can see that the experiment itself, we start sliding, reach the peak, then go into some steady state. I put up a 10-second hold. Look at the blow up over here. Friction relaxes, and then I start to slide again, and I get this delta mu, this peak in friction, once we resume sliding. Okay? Do it over and over again with both the three-sided pyramid, this type of indenture, and also with a spherical indenture, so with different stress field. And what we see is...
Was that an FM-ish to the right?
Yeah, this is, I can't remember, this is someone in Texas did for me. I think, I can't remember what he did. Okay, so what we find out is that the diamond, that when we do these scratches in diamond on quartz, that the frictional aging delta mu does not really change with hold time. Hold time does not seem to be doing anything, and we definitely don't see the linear increase in frictional aging with the hold time from previous experiments. This is diamond on quartz from the nano indenture. This is quartz on quartz from centimeter scale experiments from Bieler et al. This is despite the fact that contact area grows linearly with the hold time. This is 4 different holds during the hold. You see I put here a slope about 0.03. And contact area is normalized by the contact area at the beginning of the hold. You can see it increases linearly for 1 to 1,000 second holds. So we're missing a key physical mechanism here. And you guessed it maybe, that the key physical mechanism is what we call the strength, the contact strength. That's the chemical bonds, right? This is a diamond, and they don't really want to interact chemically with their surroundings, let alone a silicon oxide. So we don't really form any meaningful, I won't say any, but any meaningful chemical bonds between the tip and the sample. And the interpretation here is that we're lacking this inherent frictional resistance from the chemical bonds. And really the contact area works together with the chemical bonds. I mean, contact area alone is just nothing without having any physical mechanism, any chemical mechanism that actually makes use of this contact area. So frictional healing emerges from the coupling of both contact area and the chemical bonding. And this is again the siloxane bonds that I'm talking about. Silicon through oxygen to another silicon across the interface. Think of an interface around here. Okay. So next up, we want to see if we can, okay, this is all consequential, and I want to really convince you that chemical bonds are responsible for that behavior that I just showed you. To test whether chemical bonds are really what's controlling this behavior in quartz and diamond quartz, I've done some adhesion tests or pull-off tests. The idea is pretty simple. This time we're using the uniaxial nano indenture just because we can push harder with a one axis. And basically I do a loading and then an unloading on the sample. The first stage is loading. I load the tip. This is the nano indenture tip here in light blue. I show here a spherical tip or a sphericonical. It's a cone ending with a sphere. And it indents into this sample right here. We reach some indentation depth and there's some contact area, and we know what the contact area is. And then I unload the whole setup, and I see that when I reach zero load, right, I'm not putting any force on the tip. I need to pull a little bit. I need to go a little bit into the negative side of load and pull a little bit on the tip because it's kind of stuck on the sample. It's kind of adhered a little bit to the sample. That's an adhesion test. I can this adhesion force. This is the force required to detach or start detaching the tip from the substrate. Of course, this is an exaggeration. It doesn't really look like that. But that's what I'm talking about. The adhesion is dependent on the contact area, obviously, and the bonding that occurs between these two solids.
It's still diamond.
Well, yes, but we'll go back into that in a bit. The thing is that we have this is a very simple stress field. We're just pulling on it. So when there's no shear, that kind of complicates things and makes it a bit more hard to interpret. And also, contact area during the pull-off doesn't really grow. It can only decrease, right? So contact area grow is disconnected from this process. So we can really look into the contact strength. So let's look at the testing matrix here. Starting with the nanoindenture tips. We use two types of materials, our chemically inert diamonds and a chemically active quartz tip. And this is an example of a quartz tip. It's hard to see because I just took a picture with my phone. It's not really good. I bought these synthetic quartz single crystal wafers. I cut them down to really, really small rods. And I shipped them to a company in Switzerland, and they were fantastic, and they were able to make these quartz tips. And they made it for us with two geometries, a sphere and a three-sided pyramid. That's Berkovich. So this is an example of you can't really see the tip. It's a quartz Berkovich tip. So we have basically diamond and quartz, each of two different geometries, and the substrates are all going to be chemically equal. So SiO2, I'm going to use natural quartz single crystal. I'm going to use synthetic quartz single crystal made from the same material. That's the same material that we use for the tips. I'm going to use synthetic fused silica, which is kind of like commercial glass. And it's amorphous, right? It's a glass. They're all chemically equal, but they have a little bit different structure. That's our testing matrix. An adhesion test kind of looks like this. Let's start with the diamond on quartz. We're starting at 0. This is the load on the y-axis and indentation depth at the x-axis. You can see we're starting loading up the sample to a prescribed load, 40 millinewtons, and then that means that at the peak we have a contact pressure of about 13.8 gigapascals. Okay? The diamond is really, really stiff, it doesn't deform, and we can really get to high stresses. And then I unload the sample along this curve, and when we reach this point where 0, that's where adhesion plays. Same thing again with quartz. It looks a bit different, but the same procedure. This time you see that the contact pressure is much smaller, 1.32 GPAs. Unload the thing, it kind of looks funky, but what happens, what's the point of interest is really what happens over here. And they're all done at the same rates. And you can see, and the close-up of this region is in this frame, and you can see that there's a minima, and we're in negative load. So we actually have to pull on the nanoindenture tip to start detaching it. I told you that we know the contact area during as a function of the indentation depth for different materials. This is a log scale, and I've done this a bunch of times with the different geometries and the different substrates to get a general trend. And what I found is this.
Wait.
Yes.
Can you go back?
Yes, of course.
What does this plot, this hysteresis plot show actually? You go to zero depth at around 1,000 nanometer when you're unloading, okay? And what happens then? You do a negative load to pull it? What is this flat line that goes along
So,
the
yeah, it looks flat. It's not really flat. It's just the scale is, I mean, we're starting talking about 0.02.
Oh, so this
Okay,
is
it looks
negative.
flat. It's not really flat. It just changes angles. It's because we're starting to pull it apart.
So you're unloading it at a constant
Right. Yeah, and I continue.
constant rate.
Yeah, and I continue pulling on it. Yeah, unloading it at a constant rate.
So you're measuring the force that's needed to move at a constant rate.
Yes, exactly. Oh, sorry. Okay, so I've done this a bunch of times, and I found out this. I get two trends. The red group is our chemically inert diamond on quartz or diamond on silica, and the blue group is quartz on quartz or quartz on silica. And this is experimental data. It's quite messy. These experiments I'm not saying they're clean. I've done them as clean as possible in terms of chemistry and contamination, but they're not like, it's a very subtle signal. What you can see here that they follow very different trends. Triangles are the sharp triangle, pyramid into the flat. The circles are the spheres into the flat surface. And we see that the adhesion force versus the contact area at the point of adhesion. So the force is really loosely dependent on the contact area for the inert diamond quartz contact, but kind of follows this interesting trend where the force is proportional to the square root of the contact area for the quartz-quartz contacts. Okay, you also see that obviously quartz-quartz adhesion is higher than the inert diamond quartz. What's going on here? Okay. I need to convince you that chemical bonds are responsible for this adhesion that we see. I'm going to approach this through fracture mechanics prediction, and then also do energetics calculation from bond energy. The reason I'm going to fracture mechanics is really because of the scaling that we see from the blue data set, where the adhesion force scales in general with the square root of the contact area. That means it scales with a length scale. And if the projected area of the contact is circular, it would scale with the radius of the circle. That means that the force is really dependent on edge effects of the contact. We are detaching the contact, the nanometer tip from the contact at the edges, not all at once, but at the edges. We're kind of peeling it off from the edges. That's what we're going to learn from this scaling. And if you think about adhesives like adhesive tape, when you're going to put it on the table and you start pulling it on it, it doesn't come all at once, right? It kind of it goes. It's always an edge effect, right? If you look at it from the side, it kind of looks like a mode 1 crack, right? We're going to propagate a crack while I'm pulling off this tape. Same idea. Okay, if we think of adhesion or pulling off the contact as a mode 1 crack, then we can kind of think of the work needed to detach or start detaching the nano-indenture contact as the critical energy release rate, G. Energy release rate is just the work required to start propagating a crack or extending a crack in mode 1. And in mode 1, that is what we know from fracture mechanics. It equals, it's a function of the fracture toughness over the elastic modulus of the contact. If we equate W with G sub C, I come with this equation where I can estimate the fracture toughness from my experiments, where I can calculate W. I know what's elastic modulus because I can just measure it with a nano-indenture. and I know it is, 114 GPAs for quartz. And I can get an estimate of the work of adhesion using contact mechanics and the Johnson-Kendall-Roberts model specifically. This is only valid for my spheres on flats. It's not going to work with the plastic contacts with the pyramids. So if I take only the data from spheres on flats, I can calculate the work of adhesion using this model. It dependent on the force of adhesion divided by the radius of the sphere with other parameters. Radius of the sphere we know, and I can infer the fracture toughness from my experiments, from my adhesion experiments, and you can see that it falls well within the reported range for quartz, 0.72 MPAs times meters to the power of half. It falls within the range. And when we propagate a crack, we open up a crack in quartz, then we inherently break silicon oxygen bonds. So this is the first reason to start believing that the adhesion that we see from nanodentation tests is coming from breaking and rupturing silicon oxygen bonds. Okay, let's get some more. Let's do another calculation and go to bond energy. So I can estimate the work necessary to break silicon oxygen bonds. If we assume that all the bonding sites on the surface are in use. What do I mean? Think of a quartz or a silica surface. There's bonding sites available at the surface. If we assume that all of them are going to be used in a unit area, then I can estimate the work needed to rupture all of them. And so, within that area. So the work necessary to break silicon oxygen bonds is dependent on the bond density. And this comes from chemistry. It's called Zhuravlev's constant. There's about 4.9 times 10 to the 18 bonding sites per meter squared. Chemists are really useful, and they know the change in Gibbs free energy for rupturing or forming bonds, different bonds. So for silicon oxygen bond, that's about 450 to 500 kilojoules per mole. And this is just Avogadro's number. And when I do this calculation and I compare it to the work of adhesion that I get from my experiments, I see that they're kind of close together. This is a log scale, this y-axis. This is the work of adhesion in joules per meter squared. They kind of match up pretty closely. This is the mean. This is and plus minus 1 standard deviation from my sphere and flats contacts. If I do the same thing calculation with assuming hydrogen bonds, capillary bridges, or van der Waals interactions, I don't get nearly enough work of adhesion to explain this behavior. Okay, so close up now. So I've shown you that contact area alone is not enough to explain frictional aging in rocks. And that chemical bonds are necessary ingredient in that code. You also seen that quartz-quartz adhesion is greater than chemically inert diamond quartz adhesion, and the reason for that is that interfacial bonding, silicon oxygen bridges, is the aging mechanism. The problem is that this physics is lacking in almost all friction models today. The molecular interactions, I hope I convince you that molecular interactions matter and affect, well, I won't say the whole fault, but they affect the small bumps in a small scale roughness in natural faults, and the small scale roughness in nominally flat rock friction experiments, where we derive all the friction laws. So the molecular interactions matter, and it's really important because the small bumps on the faults, they live on top of the big bumps in natural faults. There is a fractal pattern to the roughness of fault, And so they're everywhere. As I said, rock friction models and relationships really need to be revised because they're just not capturing the full physical behavior that we observe in the lab. That means that we include some error or we have some uncertainty that we introduce into these models when we go into more complex geological settings. And more broader impacts from this work, the fun thing about working with fundamental science and friction is really, really a fundamental process, is that it goes into different parts of life and science and engineering. And I'm talking about geoengineering. More and more fluids are getting stored and injected into oil reservoirs and gas reservoirs. And while it's great and a very important solution to fight climate change, and it doesn't come without any risks and hazards. And they form, and typically injection can cause a lot of man-made earthquakes. So places like Oklahoma, which kind of sits at the middle of the North American craton, and they're not prepared to deal with earthquakes, suddenly between 2010 and 2015 started to live in a place that has a lot of seismicity, even more than California, and this would be quite big, like magnitude 5 earthquakes. So maybe maybe California and San Francisco are okay, magnitude 5, it's kind of alarming, but we can deal with that. But these places, they are not prepared for these types of earthquakes. If by our understanding of friction and how it changes, what controls it, if we can make these earthquakes, and they're going to happen because this is happening. People are injecting CO2 into the reservoirs. If we can make like magnitude 5 earthquake into a magnitude 3 earthquake, that's pretty good. That doesn't disrupt people's lives and causes damage to infrastructure and cause casualties. Moreover, more locally speaking, in Israel, we always think about the Dead Sea transform, and it's really interesting and important for us. But I think looking to the future, the shoreline and the whole shoreline is really a strategic resource or a strategic part of Israel, because we have a lot of population around the shoreline, and there's strategic infrastructure like civilian seaboards or military infrastructure, underwater communication cables, and energy infrastructure in the sea. And a lot of work has been done by Oded Katz and other researchers into the submarine landslides, that these types of, first of all, landslides are a friction controlled process, and they can disrupt and cause a lot of damage to these types of infrastructure, and they are really, really important to our security as a nation. And so trying to understand the frictional process of these types of geological phenomena and trying to mitigate the risk, or at least map out the risks, is extremely important for future development and security of Israel. So with that, I thank you, and I'm happy to answer any questions.
Questions?
First of all, really, really interesting talk. Very nice work. Second, I want to ask, Tzachi wrote me that he's at home with a sick child, and therefore he's looking at you from the laptop, but he wants to ask a question. He says the work is very interesting, and he's asking what happens at high temperature and at larger contact area. And I'm adding to that what happens at larger loads, because this aging has a specific strength to it, a specific change to it. And as you change the normal load, it will become less and less important as a fraction of the shear load.
Yes. So yeah, the shear resistance just from adding more and more load is important. And I haven't even studied that yet. That's kind of like the next step. That 2-axis nano inventor I showed you where I did my scratches. About a year ago, it was just before Christmas in 24. I had the quartz tip ready in Texas, about the quartz sample, and we were ready to plow into that. But then there was a problem with the machine, and we couldn't do those experiments. So I really don't know what's the contribution of the chemical bonds that happen when we introduce shear and more normal stress. It's still kind of, we're at the edge of what we know right now, and I'm really trying to push the boundaries in the friction community. And so I have no answer to that. But if we increase temperature, and if we increase temperature in contact area, and more load, first of all, when we put more load and higher pressures, we're going to get pressure-assisted bonding. It's going to help overcome energy barriers, so we might get more bonding there. And temperature as well, right? We're going to increase the reactivity of the chemical species and get more bonding. But again, this is open questions that are the natural continuation of this work, and I really don't have any answer to that at the moment.
Thank you.
Nir, nice talk. I wonder, this is a basic question. Why still you use these flat surfaces when we know that, as you said here, faults are rough? They are not only rough, they are interlocked. Meaning that surface area is not, at least not defined well when you talk about interlock surface, fractal, or surface that their roughness is larger when the scale is larger. So I think that radial state in general is nice friction theory, but I don't understand why it has something with earthquakes.
Just to start off, I'm not into radial state friction as well. I know that there's a lot of limitation to this idea and just working with flat surfaces. First of all, working with a flat geometry is helpful to simplify the problem and really get into the physics themselves. Because when you introduce a lot of heterogeneity, it's going to be very difficult to tap into what the physical processes are. That's the first thing. But as you know, earthquakes really are when we can have a broad area that kind of slips it all at once, where we can also see small patches. And the small patches, you can think of them like a pulse-like rupture, right? They only rupture a small part. So the roughness doesn't necessarily roughness of natural faults doesn't necessarily have to affect the whole process of rupturing a whole fault. It can be very localized. And in these localities, roughness might not be very rough. It can be kind of smooth. And yeah, your work too showed that there are all these very shiny and flat surfaces and faults as well. So it's a complex question. We have both living in the same seismogenic environment, and it's interesting. It makes it more challenging. I agree. It's not as simplified as using flat surface, but I would also argue that as we go deeper and deeper into the Earth, we have higher temperatures, plastic deformation starts to be king, then we're gonna start deforming and flattening out a lot of this roughness. Not all of the roughness, but some of the roughness is going to be flattened out from the high temperatures and the fluid-assisted deformation we have at the depth. So I think at least at mid-crustal ranges, lower crust, definitely when we're thinking about subduction zone earthquakes, we have more flat surfaces are important in these tectonic regions, and so in these seismogenic regions. And so I think they're still worthwhile to explore.
Okay. Last question.
In granular environments like the one that you showed in Oklahoma or the landslide, how fluids will change what will be the effects of fluids on your results in bonding and adhesion?
Yeah, so there is, from material science, they really look at how what happens when you have fluids, and they look at very small scales, so adsorbed layers, and that can really affect how bonding is formed. So if you have a lot of like a thick water layer attached to, adsorbed on the surface, it can really means that you have hydrogen bonding between fluid layers and not the solid themselves. But when we're thinking about faults, again, the pressures are really, really high. So yeah, we have fluids everywhere, but we also have solid-on-solid contact at some point, right? And so most of the strength is going to come from these solid-on-solid contacts. And so as we go, I think, deeper into the earth, think about where earthquakes form, live, and operate. 2 kilometer depths and up to, let's say, 12, and sometimes more. The fluids are going to be a big part of what happens during the healing. They're going to change, they can disrupt or enhance the healing. I have no idea because I haven't tested that. So definitely affect the healing, but at this point, what I can only say for sure is that the fluids will definitely have an effect during the dynamic part of the earthquake and really help weaken and dominate the response. But fluids themselves should have a chemical effect just because they're going to be saturated with different ions and different and calcium carbonate and stuff like that. So yeah, it's a lot of open questions, but I think worthwhile to test.
In relation to your experiments, if you thought experiment, will you conduct the same experiment with a layer of fluid? How would it change the change in friction?
So in AFM test, it really is sensitive. I said you change the humidity levels, you change the friction. And these, because I have such high pressures, I did these experiments also in different humidity levels. At least with diamonds, I didn't see any big differences. But again, it's worthwhile to further explore. I'm kind of banging on the fact that I have high contact pressures, and so those absorbed layers are not as important as they were. But still, I'm still not sure.
Let's thank you again.
Thank you.